Okay, welcome everyone to today's colloquium. Irfan Siddiqui's out of town today, so I'm Jonathan Worley. I'm introducing my colleague of 40 years, Joel Fajans. We met when he was a graduate student. I was a starting postdoc at MIT. I know many of you know Joel very well and have known him for decades. Some of you don't. So I have a small biography that I've written. Well, actually, that Joel wrote about himself, and I'm reading it. So anything incorrect in here, you talk to him afterwards. Joel Fajans grew up in New York, New Jersey, and Afghanistan, which is really unusual. Before getting his undergraduate, before he got his degree from MIT, he was in New York, New Jersey, and Afghanistan. He stayed at MIT both for his undergraduate and graduate work, where he worked on free electron lasers with George Bekoffy, which is exactly where I met him, working on his free electron laser back in the early 80s. He graduated in '85, winning the Simon Ramo Thesis Award and the Hertz Foundation Doctoral Thesis Prize. After a short postdoc at MIT, he had a longer postdoc with Professor John Momberg at UCSD, where he worked on non-neutral plasmas. He joined UC Berkeley as a Miller Fellow Assistant Professor in 1988, just a while ago, where he continued his work on non-neutral plasmas, nonlinear dynamics, and 2D fluid dynamics with the help of an ONR Young Investigator Award, an NSF Presidential Young Investigator Award, and a Sloan Fellowship. In 2003, Joel became a founding member of CERN's Alpha Antihydrogen Collaboration, winning in 2010 the APS John Dawson Award for Excellence in Plasma Physics. Plasma physics was actually absolutely central to the development of the technologies to trap and synthesize antihydrogen. Recently, he and the Alpha Collaboration made the first direct measurement on the influence of gravity on antimatter. So I give Joel the floor.
As an undergraduate at MIT, he was the smartest guy in my class.
There you go.
Oh, I didn't know that. You should have told me that at the time. Anyway, this project began as an argument between Jonathan and me, actually. Jonathan was coming into my office once a week for 6 months saying we should do gravity with our antihydrogen atoms. And I said, that's impossible, don't bother me, go away. After 6 months of his bothering me like this, I finally took a look at the scrawled notes that he had on the corner of his whiteboard and said, you know, that might work. And here we are, about a decade later, with more than that, 12 years later, working on this. So after Jonathan and I had it out, this became a Berkeley project. We worked on it here within our two groups for about 5 years, but eventually it spread to the entire Alpha collaboration. Alpha is a CERN collaboration of about 60 members. Now, ever since Dirac invented the concept of antimatter, predicted the concept of antimatter, people have speculated about how it would fall under gravity. There's even been speculation that it might fall upwards, though I have to say that's probably been mostly beer hall type of conversation. I think I'm going to surprise few of you by telling you that, in fact, we found that antimatter falls downwards. And since I don't have a wonderful physics result to report, instead what I'm going to do is give you a little bit of historical context about this question, talk about theory arguments about why people might have believed one thing or another, why weird gravity experiments the concept doesn't simply go away, and then I'm going to talk about some indirect experimental measurements of gravity and antimatter. Then I'm going to talk about the first and failed direct measurements, direct experiments trying to measure this phenomenon. And then I will get to how we actually were able to measure the effects of gravity on antihydrogen atoms. Now, everybody knows that apples will fall towards Earths, and everybody believes that an anti-apple would fall towards an anti-Earth. So the question that we'd like to know is what happens to an anti-apple in the presence of Earth? Will it go down with the normal acceleration of 9.8 meters per second squared? And Einstein's weak equivalence principle, of course, insists that antimatter will fall exactly in the same fashion as matter. And the weak equivalence principle has been satisfied in every experimental test to date. However, there's additional arguments that apply just to antimatter, and I'm not going to go into any of these different arguments. I don't have time. But most of these arguments have been challenged at one point or another. And unfortunately, it's cut off on the screen. But there's a paper by Nito and Goldman. It's a long paper that challenges most of these arguments, points out that there are difficulties with them. Not only that, the fact of the matter is that even on fundamental questions like this, physicists have been wrong before on these sorts of questions. For instance, about parity conservation, people believed in it, and Wolfgang Pauli said, I do not believe that the Lord is a weak left-hander and will bet a substantial sum that experiments will give symmetric results. Now, I don't know if he ever actually made that bet, but I do know that Richard Feynman made a $50 bet, a substantial sum. But not to worry, because at that point, Landau came along and he fixed up parity conservation by adding charge to it. So now we had CP conservation. And of that, Landau is rumored to have said, if CP is violated, I'll hang myself. He didn't. But in any case, I think in our generation, we've lost 95% of the universe in the last 40 years. When I first came to Berkeley as an assistant professor, Bernard Sadulay was first setting up his equipment to find dark matter. And we're still at it 40 years later. This is an embarrassment, frankly, at this point in time. Another thing that's been overthrown lately is the idea of the cosmological constant, which, as you know, Einstein called his worst blunder, and yet it turns out to be necessary for us to explain the universe. So it's a little bit arrogant for us to believe that concepts like the weak equivalence principle and, say, CPT violation are necessarily conserved, as other principles which people deeply believed in have been overthrown throughout the years. Now, we happen to know that something is wrong with the theory of antimatter. And the reason why we know this is that the Big Bang predicts that there should be just about as much matter as antimatter in the universe. And that's simply not true. There are lots of satellites which have gone looking for antimatter, and they don't find nearly a sufficient quantity of antimatter. Moreover, there have been, if you had a galaxy which was made out of matter and another galaxy which was made out of antimatter, there would be a front between them. At that front, there would be positron-electron annihilation, which would make 511 keV. Am I wrong? You're shaking your head. 511 keV, which is not observed out in the universe. So there just doesn't seem to be a lot of antimatter in the universe. And this is called the baryogenesis problem. It's a really serious problem because there's no current solution to the baryogenesis problem. There are CP violating weak interactions which do not conserve baryon number, but as far as I know, nobody has ever come up with one that is nearly strong enough to explain the baryogenesis problem. Now, if you were able to violate the weak equivalence principle, this could easily solve the baryogenesis problem. And reasonable physicists, serious physicists, have actually proposed theories based on antimatter repulsion, or at least a different gravity, to account for a lot of what we see out in the universe. Here are 3 of those series. I don't have time to go over them, but as I said a moment ago, these are not crackpot tech people. They're unlike the people that every 2 weeks or so send me an email and tell me that I don't understand anything. In any case, there are additional experimental there are experimental indirect measurements about gravity and antimatter. Some of them are listed here. Again, I don't have time to go into the details. But most of these have been challenged. For instance, there was a paper just in 2016, not so long ago, that said, however, for the antimatter, all of them exploit additional assumptions, such as the gravitational properties of virtual particles, the physical significance of absolute values of the gravitational potentials, CPT invariance, etc. Now, there's also a critique of all of these arguments in the paper that was cut off previously, this paper by Goldman and Nito. So, what do I mean exactly by a direct experiment? The previous experiments were indirect experiments, which relied on fairly obscure, subtle physical concepts. There haven't been any what we might call Leaning Tower of Pisa type of experiments in which people have dropped matter, let alone antimatter, off of the Leaning Tower of Pisa. Yes, I do know that that was very likely just an apocryphal experiment that Galileo did. But in any case, I'm going to define a direct experiment as an experiment in which you actually track the trajectories of individual particles as they're moving around inside the apparatus. And there has been an attempt in the past, it was called Fairbanks, by Woodburn and Fairbank experiment at Stanford sometime in the 60s, where what they attempted to do was to measure the effect of gravity on an electron. In other words, they dropped an electron and they wanted to see where it was going to go, and then they were going to drop a positron and see where that was going to go. This experiment is actually quite famous because it had a paradoxical result. The result of this experiment, which they only attempted for electrons because positron sources were inadequate at the time, the results of this experiment was that the electron didn't drop at all. It didn't seem to be influenced by gravity in any way. And fortunately for them, there was actually simultaneously some people knew about this experiment, and they came up with a theoretical explanation of why it would be so. But as I said, it's famous for this result. So to understand why you might think that the electron shouldn't drop, let's review what their experiment was trying to do. It had an electron inside of a metallic tube, and that electron should have dropped under the force of gravity, mg. What Schiff and Barnhill pointed out is that there are also electrons in that shielding tube, that metallic tube that's around that, and those electrons themselves would sag under the influence of gravity. How much would they sag? Well, they would sag until they made an electric field force that was pointing upwards to prevent them from sagging. And one of the things that you learned in freshman physics is that if you have an electric field which is all present in all places on a cylinder like this, that electric field is going to be also present in the center. So you would expect that this electric field, which is pushing the electrons up, would also be pushing your test electron up. And you would expect that the electron wouldn't actually fall under these circumstances. So that appears to explain this result that they had. A curious thing about this is, of course, if you have a constant electric field, there's a potential difference between the top and the bottom of the cylinder, which you might expect you could measure with just attaching a multimeter. But that ignores the fact that there are electrons inside of the leads, which were also sag. And that's going to cancel out, so you wouldn't actually get any measurement at all on your meter. Okay, sounds good, except that the situation is quite a bit more complicated than that. Because another group of people realized that there are ions. This metal is made out of some ion lattice, and the ions inside that lattice are going to sag under the influence of gravity. Now, since the ions are heavier, it's going to require a bigger electric field to keep them from falling down. And the net result is that you might expect that the electrons would actually fall down at a rate that's faster than the acceleration due to gravity. Now, these two pictures of the electron and the ions can be reconciled by doing the temperature analysis of what's going on here. But it's still a conundrum exactly what should have happened in this experiment. And it's a particularly conundrum because now we know a little bit more about what goes on inside tubes and all metallic tubes. And we know that actually the fact that it stayed stationary at all was really, really puzzling because it ignores something called patch fields. Now, one of the things that you learned back in freshman physics is that if you make a Faraday cage, in other words, a metallic tube which is covered on all sides, there's no electric field inside of that tube, right? That's one of the most fundamental things. It's also a lie, like many things that we teach inside freshman physics. And it's a lie because things like grain boundaries, oxide layers, many other possible mechanisms generate rather substantial electric fields inside of a metallic tube. For instance, on the alpha experiment, one of my graduate students, Andrew Christensen here, was able to actually measure these fields inside of our apparatus, which is similar to the Fairbank apparatus. And he measured a field of 10 millivolts per centimeter. This is actually quite an enormous field, if you think about it. For instance, if you calculate how much force it would have on an electron or a positron, you could calculate the ratio of the electrical force that you would get from this field to the gravitational force. And you find out that the electrical force would be about 10 orders of magnitude stronger than the gravitational force. So what should Fairbank have observed? He should observe the electrons going up, going down, going sideways, moving pretty fast, and he didn't observe any of that, so we don't actually understand what happened inside of his experiment. But in any case, the net conclusion that you reach from this is that it's probably impossible to do this sort of experiment inside with a charged particle. You need a neutral particle. And one of the charged particles that you could use is a neutral antimatter particle, an antihydrogen atom, for instance. And we've been able to show that an antihydrogen atom is charge neutral to a sufficient degree that we should be able to make this experiment. That was an earlier experimental measurement that we made. But you could also conceive of doing an experiment like this using positronium, which is also charge neutral. Now, just to review, in the elementary school model of what I mean by an antihydrogen atom, it's an antiproton in the center surrounded by a proton going around the outside. And there are 3 experiments that have been approved at CERN to use antihydrogen atoms to try to measure gravity. These 3 experiments have about 60 people working on each of them. There's our experiment, the alpha experiment, where we've succeeded by using a magnetic balance. There's also another experiment called G-bar, and what they want to do is actually something that's really more complicated. They want to make an antihydrogen plus ion. In other words, an antiproton with 2 positrons around the outside. The reason why they want to do that is a charged hydrogen atom is much more easily manipulatable than a neutral antihydrogen atom. And they want to cool those antihydrogen atoms down to a very, very cold temperature, strip the extra positron away, and then make a fountain. And then finally, there's an experiment called AEGIS, which intends to make a deflection measurement of an antihydrogen beam using an ultrasensitive particle detector. Neither of these other 2 experiments have made a great deal of progress, but they're coming up behind us. Now, why is it that a gravity measurement is actually hard? There's the neutrality problem, of course. But the other problem is that our antihydrogen atoms have an energy of somewhat less than half a Kelvin. That's really very cold. But if, say, the average antihydrogen atom has an energy of about, say, 0.3 Kelvin, that means that it's going to be traveling at a speed about 70 millimeters per second. So let's consider an experiment. Let's say you took an antihydrogen atom at 70 meters per second and you just threw it upwards like it was a baseball. How high would it go? Well, the answer is that it would go up about 250 meters, which is coincidentally about twice the height of the famous fountain in Lake Geneva next to CERN. Unfortunately, I haven't found a funding agency yet that's willing to fund a 250-meter superconducting magnet, so we have to be a little bit more clever than that to measure the effect of gravity with our antihydrogen atoms. And for the remainder of the talk, I'm going to be describing how we actually make this measurement, but it's worthwhile starting out by talking about where we get the particles, in particular, where do we get the positrons. Now, of course, Carl Anderson, who was the discoverer of the positron, found them in cosmic rays, but we use sodium-22, which is a very energetic, very productive source of energetic positrons of about 100 keV. 100 keV is not very useful for us. It's way too energetic. So the very first thing we do with these positrons is that we send them into a moderator made out of solid neon. They rattle around a little bit in the moderator, and they start to thermalize on the solid neon moderator. Now let's take a side trip for a second and talk about work functions. If you have a metal, there are electrons in it, they have some energy. Why don't they pop out of the surface? They don't pop out, of course, because there's a work function, which is not precisely, but it's like an electric field which pushes the antihydrogen atoms back into the metal. And that's, I don't know what I just said, it pushes the electrons right back into the metal. Now, that's because the electrons have a negative charge. If you put a positive charged particle in, that same work function is going to pop them out of the metal. So out of this solid neon, we're going to get positrons popping out, which have an energy that's about equal to the work function, or about 1 eV. We can channel those positrons into something called a circo-positron accumulator. And I don't have time to go into how these devices work. They're the basis of almost all positron research these days. But in a few minutes, we can accumulate about 10 million positrons every couple of minutes and eventually transport them to something that we call a Penning-Malmberg trap, which will keep them around for a very long time. So what is a Penning-Malmberg trap? A Penning-Malmberg trap is a series of cylinders which are electrically isolated, and you can impose voltages on those cylinders. What you can do is make longitudinal wells. And for instance, if you make a negative going well, that's going to attract positrons like that. While if you make a positive going well, that's going to attract antiprotons. You can put these two wells next to each other. So you can get your positron, what ends up being a plasma, right next to the antiproton plasma. That doesn't explain why they don't pop out in the radial direction. After all, the positron plasma has a fairly substantial electric field, which is pointing radially outwards because it's got a fair amount of charge inside of it. But we use a magnetic field which points along the axis to keep the particles from popping outwards in the outwards direction. And that causes the plasmas to E cross B rotate. What actually happens to them, looking end on, is that you see that the plasma will sit there spinning, and it will spin like a rigid rotor of uniform density if it's sufficiently cold. So we can easily store particles inside of these things, and these are immensely great traps, actually. We can keep particles around for a long time. In comparison, for instance, if you talk about fusion devices, the biggest fusion device in the world is ITER. It costs upwards of $20 billion. And there are venture capital has invested about $6 billion in fusion in the last couple of years. And at best, they can keep plasmas around for perhaps 30 seconds. Whereas our devices, which are about 10,000 times cheaper, can keep plasmas around forever. Of course, there's a cheat. And the cheat is that we have much lower densities and we have much lower temperatures. But nonetheless, we can do things in our devices which you could never dream of being able to do inside of a fusion devices. Curiously, it just turns out that charged plasmas are easier to manipulate than uncharged neutral plasmas. And I'd like to go through a couple of the things that we can do with our plasmas. For instance, one of the things that we need are very, very cold positrons. We can get that naturally because there's this strong magnetic field surrounding the plasmas. And that's going to cause the electrons or positrons inside of our plasma to go around in cyclotron orbits. Since they're going around in a tight little circular orbit, they're going to radiate their energy away. And at 1 Tesla, they radiate their energy away with a time constant of about 4 seconds. Now, that means that the temperature should start to exponentially decrease, and it does. But it always gets hung up at a temperature of about 100 Kelvin. This is true in all of the devices that are built like this. They never get colder than 100 Kelvin, which is really surprising because you might have expected them to cool down to the wall temperature of their surroundings, which is typically liquid helium temperatures, or 4 Kelvin or 10 Kelvin or something like that. They simply don't do that. So we need to get to colder temperatures, and one of the techniques we can use to get to colder temperatures is we can put our positrons inside of a well, and then we can evaporate them. All we have to do is lower one of the well's barriers, and the hottest positrons are going to escape. What's left behind is cold, and so the whole thing cools down just like in any evaporative process. This can get us down to temperatures that are around 10 Kelvin, which are low enough for what we need. It's a temporary effect, because as soon as the evaporation is over, they're going to start to warm up. We have about 1 second to use them in this condition, but that's long enough for us to accomplish what we need to do. Another thing we can do with these plasmas, which you could never do with a neutral plasma, is along these cylinders that are making our longitudinal walls, we have azimuthal patches, which are electrically isolated. By applying the right voltages on these patches, we can make a potential which rotates around, an electric field which can rotate around in a circle. Now, remember, the plasma itself is also rotating, and under certain conditions, we can lock the rotation of the plasma to the rotation of the externally applied electric field. And that's really convenient, because there's a really simple formula that tells us what, for instance, the rotation rate is and the density, and relates it to the density of the plasma. By changing the rotation rate, which we can do by changing this frequency over here, we can change the density of our plasmas at will, something that turns out to be very convenient in our plasmas. Another thing we can do is to use more freshman physics. We can calculate what the potential is of the plasma on its axis. If it's a constant density plasma, which in general it is, that formula for the on-axis potential when it's surrounded by some metallic wall is this formula, which you probably recognize from your freshman physics classes. Now, there's only a couple of variable parameters here. There's the wall radius, but that's fixed because that's just a piece of apparatus. So the only parameters left are the plasma radius, the density, and the on-axis potential. So if we could control two of those things, we're going to control the third. In fact, we're also going to control the total number of particles inside of this plasma. And to do that, I've actually already told you how we can control the density. We do it with these rotating electric fields. And I've also hinted out how we can control this central potential. Because when we do the evaporative process, particles will evaporate only when they get so that they're equal, their potential is equal to the potential that comes from the vacuum on the outside. So we control that, and that allows us to fix the plasma radius. That uniquely specifies what the plasmas look like, so we can make identical plasmas each time. And you can see some evidence of that over here. Before we learned how to do this, the plasma densities, and this is actually the total number, were fluctuating by about 30%. But as soon as we applied this technique, which we called SDR-EDC, then the plasmas were uniform to about 1%. This was a great innovation and allowed us, through a chain of events, to increase our trapping rate for antihydrogen atoms by about a factor of 40 when we were all done. It was accomplished by my graduate student, Celeste Caruth. She had a rough time with doing this because nobody really believed that it was going to work except the two of us. So she was only granted time on the machine for an entire summer from 11 p.m. at night to 7 in the morning. Nonetheless, she got it to work, and as soon as it started to work, the entire collaboration adopted this method more or less instantly. So where do we get antiprotons? Well, you know that the main job of CERN is to run particles in the LHC these days. The LHC needs to be freshened up with a new charge of particles about every 10 hours. It takes a whole accelerator complex to generate enough particles energetic enough particles to inject into the LHC. And this only, as I said, has to happen once every 10 hours or so. So you might think you could just run this complex once every 10 hours. That doesn't work at all, because it would just cool down and drift, and you'd never be able to get anything unless you run the complex continuously. So this is always running, but most of the time it's not doing anything at all for the LHC. And in fact, we run parasitically, getting a bunch of anti-energetic protons every 100 seconds off of all of this running. We don't need all of this apparatus to get our protons. We only need a very small part of it fed into what's called the antiproton decelerator over here. I'm not going to discuss this in any great depth, except to say that part of this complex is a proton synchrotron, and the proton synchrotron has been in continuous operation since 1 year past my birth, which is really remarkable for an accelerator to be running that long. In any case, we need to take those protons. They get sent into what's called the antimatter factory through an underground tunnel, and they impinge on an iridium target, which creates a shower of secondary particles, including some antiprotons, which have an energy of about 30 GeV. This is actually the same process that was used by Chamberlain and Segre here in Berkeley in the 50s to discover antiprotons. And here's just a little bit of a personal story. Segre came to my job talk, which happened to be in this room a long, long time ago. And he came up to me and asked me if I was related to a buddy of his who's got the same last name as mine. We're not related. I said as much, and he nodded, and then he went and sat down. He actually sat in this seat over here. Yes, I do remember. And why do I remember? Because he snored through my entire talk. Anyway, that's all to say for you postdocs out there, you don't have to impress everybody on your job committee. Even the Nobel Prize winners, you can still get a job if they snore through your talk. In any case, the antiprotons are then sent into this antiproton decelerator, which is basically just a reverse synchrotron. Then they're sent into a newish ring called the Elena ring and slowed down to about 100 keV, and then injected into our experiment, which is this experiment over here. 100 keV is still a little bit too fast for us, too energetic for us. We send them into a degrader foil. Many of them annihilate inside the foil. Many of them go through with too much energy, but a certain fraction of them come through with an energy of less than about 5 keV. And we trap them inside of our apparatus using a barn door trap. We have a trap that has two walls like this. We lower one of the walls. We allow a bunch of antiprotons to come through. They bounce from the far wall. They come back, but by the time they come back, we've closed the door on the far side, and they're trapped inside. So that's our positrons and our antiprotons. Most of the trouble with this experiment is actually making the right antiproton and positron plasmas. This is an effort that since the beginning of the alpha experiment sometime in the mid-2000s, we spent at least 50%, I would say, of our experimental time trying to improve the plasmas that we use to make the antihydrogen. And we need to get the positron plasmas in particular into a shape which is quite similar to a sewing needle in shape and size. But in particular, we have to get them very, very cold. And that's really very, very hard. But once we're all done, we can put an antiproton plasma next to a positron plasma inside of our apparatus, and we can actually get that antiproton plasma quite a bit closer. How do we actually get the antihydrogen from the two types of plasmas? Well, we've stored both of them next to each other inside of a Penning-Momberg trap, and then we use three-body recombination. In three-body recombination, if you can get an antiproton close enough to two positrons, in some cases, one of those positrons will be captured, and the other positron gets thrown off, carrying away the excess momentum and energy. And how do we actually get that mixing process to happen? Well, we electrostatically tilt the trap and force one of the antiprotons into the positron plasma. They form the antihydrogen atoms by three-body recombination, but of course, the antihydrogen atoms are charge neutral, so they're not trapped by the fields of the Penning-Momberg trap. We need to have some additional traps additional magnetic fields to trap them. And what we do is take advantage of the fact that antihydrogen has a small magnetic moment, which means that it can be trapped inside of a magnetic minimum, inside of what's called a Yaffe-Pritchard trap. And we use mirror coils to create an axial minimum inside of our trap. We use an octopole magnet to create the radial minimum. And what we wind up with is basically a bathtub, where the magnetic field is lowest in the center of the bathtub, but if we go out in any direction, either radially or axially, the magnetic field is going to increase. And then because of the gradient force on a magnetic moment, that will repel the antihydrogen atom back into the trap. It will stay inside of the trap forever so long as it doesn't spin flip, and I could discuss it later, but they don't spin flip. So basically, this is a perfect trap for our antihydrogen atoms. The magnet that we use, this octopole magnet, is a state-of-the-art magnet, and it produces a field of about 1.5 Tesla, which sounds like a lot, but unfortunately it isn't, because the magnetic moment of the antihydrogen atoms is fairly small. The trap depth is only about half a Kelvin, or 40 microelectron volts. And this has to be compared to the potential drop across one of our positron plasmas, which is about 1 volt. So the natural energy scale inside of this problem is about 1 volt. And somehow or other, we have to tip the antihydrogen, the antiprotons, into the positron plasma without acquiring any of that 1 volt, keeping its energy below 40 microelectron volts. And that's why this is a hard thing to do, to trap antihydrogen atoms, is to keep the energies that low. Here's some very early data that we took. It very much depends on the positron temperature. So when the positron temperature is about 70 Kelvin, we were only trapping 1 antihydrogen atom in every 30 attempts or so. Each attempt took about 15 minutes. So basically, it was almost impossible to optimize this process. But when we were able to get the temperature down to about 40 Kelvin, we were trapping 1 antihydrogen atom in almost every attempt. And then these are just, at the time, predicted values, but we predicted that if we could get the temperature down to 10 Kelvin, we would trap 4 antihydrogen atoms in every attempt. That turns out, very curiously, to be a pessimistic prediction. And in fact, when we actually got all of these things to work, including, for instance, Celeste's SDRAVC, we can trap about 40 antihydrogen atoms in every trapping attempt, which now only takes about 5 minutes. So we can trap a lot of atoms inside of our machine if we can make the plasmas cold enough. The actual alpha superconducting magnet is extremely complicated. There are about 30 superconducting magnets inside of it. There are about 1,000 wires coming out of this system, and fortunately, I was only required to wire about 50 of those wires, so I'm very grateful to the rest of the team, which might have included Andrew, I'm not sure. Yes, it did include Andrew, to wire the rest of these things. But in any case, for the purposes of this experiment, this discussion, we only have to concentrate on 3 of the magnets. What we call the top mirror, what we call the bottom mirror, and also one of these octopole magnets running from here to here. The rest of these magnets are used in the preparation of the plasmas, this very difficult thing that I was describing a moment ago, and they're also intended for future higher precision measurements of gravity. So what happens? Each mirror makes a bump, a stronger magnetic mirror, a magnetic wall, if you will, at the position of the mirror. Here's the mirror at the top, here's the magnetic wall at the top mirror, here's the magnetic wall at the bottom mirror. And there's also the octopole magnet, which I'll discuss more in a minute. It's important to note that this makes a magnetic well because it's not in a Helmholtz configuration. So there's a minimum in the center of the system. And if we put an antihydrogen atom into this system, what it's going to do is bounce back and forth in this magnetic well between these 2 positions. Now, the octopole magnet plays the very important role of stopping it from crashing into the sides, but I'm not going to discuss that further or much further inside of this talk. It's a really complicated orbit that the actual antihydrogen atom takes. And another graduate student who's also sadly cut off over here, Adrian, who is here, worked on that problem quite a bit to understand it, but it's not so germane to the, once we have them trapped, it's not so germane to the gravity problem. So of course there are multiple antihydrogen atoms inside of our trap, and they all have different energies. And the more energetic ones are going to penetrate further into the trap, into the mirrors, than the less energetic ones. They're going to have a more more energetic ones have a longer excursion inside of the trap, so they're going to bounce back and forth. It's not a harmonic well, so they bounce at different frequencies. And the next thing that we do is we lower the magnetic field coming from the top and this bottom mirror. Instead of having a peak that's that high, we make it just a little bit lower. And when we make it just a little bit lower, the excursions are going to lengthen so that the most energetic one is penetrating fairly far into the mirror coils. In fact, it's going to go into the mirror coils and it's going to come to almost a stop there before it turns around. In fact, if we time it just right, it will come to a stop inside one of these mirror coils. It could be the top mirror, it could be the bottom mirror, just a momentary stop, but it's going to take a pause there. And even though the potential well is quite deep still, then the very small gravitational potential will add to the total mirror potential, perturbing them and slightly lowering, if gravity points downwards anyway, slightly lowering the total potential at the bottom mirror and slightly raising the total potential at the top mirror. This means that as this thing is bouncing up and down, it can just sneak out of the bottom mirror due to the fact that the gravitational potential adds to the magnetic potential and makes a slight hole. When it sneaks out, what it's going to do is it's going to come out and it's going to annihilate on the wall. And the other atoms are still going to be inside the trap. The lower energy atoms are inside the trap, but that's okay. We continue to lower these magnetic coils, and eventually they too will penetrate deeply into the mirrors and undergo this selection process where they sneak out either the top or the bottom of the trap. Now, of course, if the gravity pointed upwards, then the antihydrogen atoms would come to a stop at the top of the trap, and the mirror potential would be, well, would be lower due to the gravitational potential, and what would happen is the antihydrogen atom would sneak out the top of the trap where it would annihilate. And all we have to do is count whether or not it went upwards or downwards. Here's a simulation that was made for us by the National Science Foundation. It's actually a cartoon, not a simulation. There's a large number of antihydrogen atoms in it. As we lower the mirror coils, their actual extent gets larger and larger, and eventually they start to escape. If gravity is downwards, we'd expect more of them to escape downwards than escape upwards, but some of them will still go out downwards. Eventually, all of the antihydrogen atoms inside of the trap will escape the trap, and we'll get a final count in this cartoon, 37/51. But in the real world, what we got was 95 antihydrogen atoms fell downwards, while 37 of them fell upwards. That means that about 73% of them, 72% of them fell downwards. Now, you might have expected that 100% of them should have fallen downwards. But that's not the case, and there are a number of reasons for this. First of all, the mirror ramp rate isn't entirely adiabatic. So some of them just coincidentally get to the wrong mirror first and manage to escape there. But a more important thing is that it turns out that the magnetic balance changes as you go off axis. You only have perfect balance if you're exactly on the axis. If you go off axis, the balance is slightly different, and some of them are going to escape, following some of the complicated dynamics for the off-axis orbits that Adrienne investigated. And on top of that, there are statistical and systematic errors. So we actually extensively simulated the system, and we just we predict that 83% of them should have fallen downwards. Now, 83% isn't 72%, but it's not that far from the case. So you might think that we're done, but we're hardly done here, because this isn't an experiment yet. This is a single point measurement. You need some knob to turn to be actually able to prove anything. Fortunately, we do have such a knob. We can deliberately offset the balance between these two mirrors, making what we call a magnetic bias. For instance, we can make the top mirror stronger than the bottom mirror, and that's going to repel antihydrogen atoms from escaping at the top, make them more likely to escape at the bottom. We call this a positive bias. On the other hand, we can make a negative bias where we increase the bottom mirror, so that's going to force the antihydrogen atoms to escape at the top of our system. The natural scale for this, the basis bias unit, is G, actually, and 1 G corresponds to 4.5 Gauss. What does that correspond to? Well, if you calculate what the gravitational potential difference is between the bottom mirror and the top mirror, that will be exactly equal to a magnetic potential difference of 4.5 Gauss. So that's where that unit comes from. Another thing you can do, by the way, is to make an equilibrium bias, minus 1 G, where we make the bottom mirror 4.5 Gauss stronger than the top mirror. In that case, gravity and the magnetic potential are exactly canceled, and there shouldn't be any preference for the atoms to go up or down. We can try this experiment at all sorts of different biases, and the data is shown here. This is the bias that we're using. At 10 G, we expect everything to go downwards, and indeed, that's what we observe. At minus 10 G, we expect everything to go upwards, and that's what we observe. If you go to the 0 G, no bias case, where the magnets are exactly similar to each other, you would expect that they would to see, well, that's the 72% that I was talking about earlier. And if you go to minus 1 G, this value over here, you would expect that equal numbers of antihydrogen atoms would escape upwards and downwards. It's a little hard to do any analysis on this graph. This plot. It's easier to do it if I show it on a graph. So our data is these points over here with appropriate systematic and statistical error bars, and our simulation curve is this red curve over here. It's not a perfect match, to be sure. But on the other hand, we can simulate any form of gravity. For instance, we could simulate what you might call repulsive gravity, gravity that's sending antihydrogen atoms or antimatter upwards. And when you do that, you get this purple curve over here, which is clearly not in any place close to our data. So repulsive gravity is very clearly ruled out. You could also simulate that gravity has no effect on antihydrogen or antimatter. That's this green curve. It's closer to our data, but clearly our normal gravity curve is closer to the data than the repulsive gravity. And as I said, you can simulate any sort of gravity. Here are a bunch of simulations. And when you do that, you can find the gravity in a simulation that best fits our data. And the answer that we found is that antimatter G is equal to 3/4 of normal matter G. Now, please don't think that I'm saying that gravity for antimatter is 25% weaker. It's almost undoubtedly taken up by the various systematic and statistical errors inside of our experiment. So that seems like it's our experiment, but it's not that easy to actually pull this off, and I'd like to discuss some of the more technical details as to what you have to do to actually accomplish all of this and get it all to work. So, for instance, one of the things you actually have to do is to control the currents in the magnets very, very closely. Remember, we have to set these biases inside the mirror coils, right? So we need to control the currents. And our design goal is to get from 1 Tesla down to, well, we definitely need to get to 4.5 Gauss, but we really need to get lower than that. So we need to be able to control the current in the magnets to about 1/100%. This is possible with a standard commercial power supply. Not so easy, but possible. The problem is that we're ramping our magnets down from full current to no current in about 20 seconds. And you can't get that sort of control out of a commercial power supply. So we had to do some extra stuff. What we had to do is to make our own external control loop, this loop over here. We measure the current, and then we feed back on that with an FPGA and program the power supply to put the right current out. But another thing we do is that we send that current through both of our magnets. So both the bottom mirror and the top mirror have absolutely identical current flowing through them. And that may not be precisely controlled, but they're absolutely identical. Now, of course, we have to create a bias. So we have an additional power supply, a tickle power supply we call a Tickles power supply, which feeds current only through the top mirror. The ratio of the currents is we're using about 70 amps to go through both of these mirror coils, and the Tickle current supply is about plus or minus 1 amp. This allows us to get the necessary control over the currents that we need to drive our magnets. But still, that's not going to be good enough. Here's a picture of our magnet under construction showing some of those mirror coils. And it turns out that it's absolutely impossible to wind a magnet, which is identical to some other magnet to 1/100%. Even when you take special precautions, like for instance, on every layer inside of these mirror coils, we would take a photograph of the position of the wires. And then we would carefully measure where each wire is, and then on the next layer, we would compensate by moving the position of the wires in the next layer. Still, it's not going to be good enough to make magnets which are identical to 1%. So what we actually have to do, obviously, is to run slightly different currents using our Tickle power supply to make sure that the magnet current fields are absolutely identical with each other. And to do that, of course, we have to have some way of measuring what field the current is going to produce using some form of magnetometry. The only trouble with that is that magnetometry standard techniques don't work in a cryogenic ultra-high vacuum environment. NMR doesn't work because the NMR samples will just freeze and we get no signal at all. Hall effect sensors don't work because it turns out that when you temperature cycle them, every time you temperature cycle them, you'll get a slightly different measurement from your Hall effect sensor. So what we had to do is to invent a new technique which we call plasma electron cyclotron resonance, or ECR magnetometry. And here's the idea. What we do is we make a target plasma. We move it into a position inside of our plasma where we want to measure exactly what the magnetic field is. And then we send microwaves at that target plasma. When we sweep the frequency of those microwaves, and when we hit the cyclotron frequency, remember these electrons are going around in tight little circles. So when we make a microwave frequency which hits the frequency which they're going around, the cyclotron frequency, then that plasma is going to heat up, and we can measure that heat increase. Since the cyclotron frequency is inversely proportional to the magnetic field, that's a measurement of the magnetic field. Sounds simple, and it isn't. And the reason why it isn't is it turns out that there are multiple heating peaks. So we have to be able to locate the heating peak which is stationary, the one that's not moving as we change other parameters in our system. In this case, what we're doing is changing the bounce frequency of the electrons inside of our plasma. The plasma electrons bounce back and forth inside of our trap. If we make the trap shallow, we get a low bounce frequency. If we make the trap deep, the bounce frequency increases, and that's what's causing these side bands to move outwards as we measure the frequencies. So we can measure that frequency, which seems good, and at some level it was good enough for the current gravity measurement. But in fact, if you take a closer look at this one central peak, you find that it too is broken up into multiple peaks. And now it's even worse because the peak we want, the stationary peak, isn't even the biggest peak. This was work that was done by Eric Hunter, a former graduate student. And in the end, he was able to measure the location of this peak to about 1 part per million. This is a spectacularly accurate measurement for a plasma physics measurement, where typically you measure things to factors of 2 or 10 at best. But this is 1 part per million, and it was satisfactory for our results. So using this, we can, I should say what's causing this splitting is the plasma is also rotating, which is also a function of how long the trap is. Anyway, using this, we can make a map of what the magnetic field looks like inside of our apparatus. We can just move our target plasma to different positions, measure the magnetic field there, and make a map that looks like this. And you might think we were done, except that we're not done. And so now I have to go back to freshman physics. You all know that if you have a solenoid with some current running through it, it makes a magnetic field, right? And you also all know that if you open a switch so there's no current flowing through the solenoid anymore, the magnetic field goes to 0. That's naive, at least for a superconducting magnet. In fact, if you remove all of the current from a superconducting magnet, you get a very appreciable field. Inside our system, we get a persistent field. These fields are on the order of 20 Gauss when we go from 70 amps down to 0 amps. In other words, from 1 Tesla to nominally 0, but we in fact get 20 Gauss. So where does this come from? This comes from the way superconducting wire is actually made. Superconducting wire typically consists of a copper matrix with superconducting filaments inside. We use an enormous number of filaments, something like 628 filaments inside of there. And that means that each of these filaments is very, 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 very fine. In fact, they're about 9 microns wide. But currents can get set up inside one of these filaments. These are persistent currents. They're going to be excited when the magnetic field changes. And the inductance, well, here's an example of one of these, the fields that we get. Actually, I missed something here. What I should have said is that the inductance of this loop is very, very small, but then so is the resistance. So the time constant can be anything, really, from seconds to hours. Here are some measurements of what those time constants look like. And these are the top mirrors and the bottom mirrors. And they do range from a long time. The only thing that saves us is that the top and bottom mirrors, since they're identically constructed, have more or less the same persistent current behavior. And also, if you go through the same current history, you're going to get the same persistent currents every single time. Otherwise, this experiment would be impossible. Unfortunately, though, it takes tens of seconds to measure the field with ECR, and we're ramping our magnets down in about 20 seconds. So we can't make our measurement on a relevant time scale. We need a faster method of measuring what the magnetic field is. And Andrew was able to develop a new technique, invented this technique with an unpronounceable name, magnetrometry, I believe is how he calls it. But in any case, what it consists of is having a reservoir plasma over here. This reservoir plasma was actually developed by Eric Hunter, but what we do is we squeeze off a tiny test particle from each reservoir plasma, from the reservoir plasma. We can do this hundreds of times and get nearly identical plasmas. Then we move the test plasma to where we want to measure the magnetic field. We measure, then we allow the patch fields to move that plasma off axis and let it go. And it turns out that it will go around in a circle, something called a magnetron motion. I don't have time to explain a magnetron motion, but you've all used a magnetron motion because inside your microwave oven, there's a device called a magnetron, which makes the microwaves which heat up your food using this magnetron motion. In any case, we can measure the frequency at which it goes around. That frequency is inversely proportional to the magnetic field, and we can get a measurement this way in about 150 milliseconds, which is fast enough for us to take real-time measurements while we're ramping the magnet down. The green curve is our desired slope, and these measurements are shown by the dots over here. They look like they're right on, but in fact, if you blow it up, they seem to be off by about 2 Gauss or so. But we can adjust for that with our Tickle current. Anyway, all of these techniques are just a sample of the things that we had to develop to make this measurement work. It's technically a very challenging problem, but in the end, we were able to make the measurement. So in conclusion, I should say that the chance that we discover something interesting is really very, very small. But the reward for discovering something interesting is really very, very high. So you can calculate the expected value for this sort of experiment. And since 0 times infinity is anything you want at all, it depends on what sort of physicist you are. This sort of experiment, I never did this until I got involved in alpha. And it turns out that I like doing this sort of experiment. They're a great deal of fun. The 20 or so years that I've been working on alpha this time has been a great way to change my career too. And I've been very happy doing it. But I would understand that some of you might think this is a complete waste of time, as is any other sort of null experiment result. In any case, we've been able to make a whole lot of measurements using the alpha apparatus. I'm only going to go through just a few of them to conclude. For instance, we've been able to measure microwave spin flip frequency. We did a crude measurement of gravity. We were able to measure the charge of the antihydrogen atom to about 1 part per billion. We measured the 1s-2s transition. We measured the hyperfine structure. We measured the 1s-2p structure, Lyman alpha structure, and we demonstrated laser cooling of antihydrogen atoms. And then most recently, we've been able to measure gravity on these experiments. This has been, well, let's put it this way. I've never published a paper in Nature before I started on this, and now we publish a whole bunch of papers in Nature, so that's been a lot of fun. In any case, it's been a big group in alpha, and a lot of people from Berkeley have worked on this. This isn't a current picture, unfortunately, but here's a list of, I think, most of the people from Berkeley that have worked on this experiment. Many of them have been undergraduates, in fact, but a bunch of different graduate students. I should say worked on this experiment for the gravity cause. Many of them worked on other experiments before. So that's the end of my talk. Thank you very much. Yes, we think about it every time. No, we can't flip our experiment vertically. What we can do, and we eventually hope to be able to do, is to put normal hydrogen inside of the machine. We can't detect the normal hydrogen at the moment because it doesn't annihilate. But that's going to be our ultimate test. You're right. We could be just systematically completely wrong. But I don't think so.
Early on, you had a slide showing how you trap the antiprotons, positons.
Yes.
How do you know when you have?
Oh, all of our measurements of antimatter is always destructive. We let them crash into the wall and we see the annihilation. And then there's a whole bunch of people, a third of the collaboration probably fully, that work on a detector which can detect those annihilations. Efficiency of the detection is quite high for either antiprotons or antihydrogen. It's around 70% or so. So we can very much tell where they went, but only destructively.
So you're using them for purpose first?
Well, in some cases, well, yes, in general, we use them for some purpose. That purpose may be merely counting how many we had inside of our trap. But all of our experiments end with some form of annihilation. In the case of the gravity experiments, we're counting whether they went up or down, because not only can we can also count the annihilations, we also know where the annihilations occurred.
Yeah, so you mentioned that you would sort of naively expect that it would thermalize through plasma, would thermalize through the wall, but then it has to go through much higher temperature. Do you
Well, curiously, we just had a lunchtime seminar in our group, which my former student Eric Hunter was talking about. And he took something which we had long speculated about, but he seems to have established that this is at least a big part of the reason. Our traps are open-ended because we have to get particles in and out. And light, room temperature radiation leaks into the trap, which establishes a radiation background inside the trap, which is different from the 10 Kelvin. He's been able to block that with appropriate filters, and that seems to help quite a bit. But that may not be the full explanation for why it happens.
Other questions? How do you prevent the antimatter from wearing away after this?
You know, if you Google online what's the most expensive material in the world, you'll find it's antihydrogen atoms. We have made hundreds of thousands, maybe millions of antihydrogen atoms, but it's just negligible in terms of, I mean, each annihilation is incredibly energetic, but the total number of annihilations is negligible. People have done calculations and claim that in CERN's entire existence, they've made enough antihydrogen to light a laser pointer for 1 second, which gives you some sort of idea of what the energy, the total amount of energy is. Obviously, if we were making more antihydrogen, we'd have to be a lot more careful.
Spin-offs. It's something you've done a lot of really great work over the way to do this.
We are searching for differences between hydrogen and antihydrogen. So far, we haven't found any. It's a null experiment. That's what I said meant by that 0 times infinity. And we've certainly been able to measure things which have set new parameters. For instance, our measurement of the positron charge is the most accurate measurement that's ever been made. It obviously should be equal to the electron charge, but it hadn't been. We've measured that to about 1 part per billion now. But so far, I can't say that there's anything that we have done that you're ever going to see on a supermarket shelf.
No, but in